Okay, class. I hope my slides are visible to you and I'm well audible to you. So, I welcome you all to the third tutorial of this course, Symmetry, Stereochemistry and Applications, which is conducted by NPTEL, whose course instructor is Professor Anshuman Roy Chaudhary from IISER Mohali. And I am Deepika, your PMRF teaching assistant. I am doing my PhD in chemistry at IIT Bombay. So till now we have completed 2 tutorial sessions for the course, and in this week of the course the video lectures which were available to you uh, contained the concepts on conformations, conformational analysis, as well as different energy profile diagrams of various hydrocarbons. Along with that, we saw stable and unstable conformations of organic molecules. So, based on the video lectures, we are going to solve a few problems in this third tutorial of the course. So, let us start with some easy questions. So, in this first question, it says conformations are different arrangements of atoms that can be converted into one another by rotation about covalent bond, double bond, single bond, or triple bond. So, when we talk about conformations, we will always involve the molecular structure in such a way that there will be no involvement of formation or breakage of bonds. Rather, we will always understand rotation along carbon-carbon single bond. That means one conformation of a molecule can be converted into another by rotating it in an angle along a carbon-carbon single bond. So that means out of all these four options, the correct option will be the option C, single bond. You can note down the explanation. Conformational isomerism is a form of stereoisomerism in which the isomers can be interconverted exclusively by rotations about formally single bonds. Such isomers are generally referred to as conformational isomers or conformers, and specifically as rotamers. As we are talking about rotation through a single bond, so these conformers can also be referred as rotamers. So this question is from the concept of the definition of conformations or rotamers. Okay, I hope this question was very easy for you. In next question, it is asking the energy required to rotate N-butane molecule about the carbon-carbon bond is called rotational energy, torsional energy, enantiomeric energy, or potential energy. So I hope you remember the concept of torsional energy, which was covered in one of the video lectures provided by NPTEL course. Okay, so in that you only have to remember that whenever we are rotating a molecule in such a way that the rotation involves 4 atoms in total, and the rotation is centered on a single carbon-carbon bond, that rotation will involve torsional energy. Okay, hence for this question, the energy required to rotate N-butane molecule about the carbon-carbon bond will be called as torsional energy. You can note down the explanation as well. So whenever we are going to talk about conformations of an organic molecule, we will always involve the concept of torsional energy. After that, now we will go through the energy profile diagram of N-butane in this question. So this question is asking the potential energy of N-butane is minimum for skew conformations, staggered conformations, eclipsed conformations, or Gauch. So if we go through and revise the energy profile diagram, the energy profile diagram of N-butane somehow looks like this. Okay, so let us start from here. The Newman projection of N-butane is represented from this first diagram, okay, where both the terminal methyls of the Newman projection will be aligned opposite or anti to each other. That means the angle between the terminal carbon-carbon bonds will be exactly 180 degree. So in this case, there is no steric hindrance present between the methyl groups. Hence, it will be in the lowest energy value of this energy profile diagram, which is drawn between energy versus dihedral angle between two methyl groups. And after rotating this staggered N-butane molecule by 60 degree, we are going to achieve at this Gauch kind of conformation. Okay, further rotation will give us these two Gauge conformations, and ultimately when we will get a conformation of the molecule in such a way that both the methyl groups are parallel to each other, in that case the energy will be maximum for this energy profile diagram. And the energy is maximum because of the steric hindrance between the eclipsed methyl-methyl groups. So, from this energy profile diagram, now we know that out of all these different conformations possible for N-butane, the one which will have the lowest energy will be the NT one, or which is also called as staggered one. Hence, the potential energy of N-butane is minimum for staggered conformation, and this is because of no presence of steric hindrance. So, I hope this question was also very easy to you. Now, let us move to another question from the conformation part. In Gauge conformations, the methyl groups are 60° apart, 90° apart, 180° apart, or 360° apart. So we just now went through the energy profile diagram of N-butane. So let us again take the example of N-butane energy profile. Okay. So in this one, if we notice the angle between the Gauge conformations, you will see that the methyl groups are 60° apart in the energy profile diagram. Okay, so if there is no mention about specifically what type of Gauge conformations are we talking about, you have to always consider the stable Gauge conformations, okay, where the methyl groups will be far apart. So out of two possible Gauge conformations, 30° and 60°, you will have to go for the conformations where the methyl groups will be 60° apart. Okay, so in Gauge conformation, the methyl groups are 60° apart, and although it is less stable than the anti-rotamer, it is more stable than the eclipsed conformation. I hope that is already clear from the energy profile diagram. Because the Gauge conformations possess less steric hindrance in comparison to the syn or eclipsed conformation. So after that, now we will talk about possible angle strain in cyclic hydrocarbons. Okay, so this question is about which of the following correctly ranks the cycloalkanes in order of increasing ring strain per methylene group. So here we will talk about cycloalkanes of 3 to 6 membered. Okay, so the cycloalkanes mentioned here are cyclopropane, cyclobutane, cyclopentane, and cyclohexane, and the ring numbers are 3 to 6 respectively. So here the question is asking which of these four cycloalkanes will have the highest ring strain and which one will have the lowest ring strain. For that, I hope you remember that cyclic molecules have a tendency to achieve planarity. Okay, so it is said that the more it is closer to the ideal tetrahedral angle, the more is its stability. And after achieving the ideal tetrahedral angle, the more it is closer to planarity, that is 180 degree, the more will be the stability. So these angle relative stability was also covered in the video lecture. So if you look at the cyclopropane ring, here you will see the ring angle measures to be 60 degree, okay, and it differs from the tetrahedral ideal angle 109 degree precisely by an angle of 49 degree. So in comparison to cyclopropane, if we move to cyclobutane, the cycloalkane ring measures to be 90 degree and it deviates from the tetrahedral angle by 19 degree. So it is also far from the tetrahedral angle, but somehow closer to it in comparison to the cyclopropane. Hence, cyclobutane ring will be more stable than the cyclopropane ring, because the cyclopropane ring will be having more ring strain. And then if we move to 4-membered to 5-membered, that is cyclobutane to cyclopentane, the angle of the ring will move more closer to the ideal tetrahedral angle, and it will differ only by 1 degree. Hence, cyclopentane will have even lower ring strain. And further, if we move from cyclopentane to cyclohexane will have a ring angle of 120 degree, which is ultimately closer to the planar angle, which is 180 degree. This is why cyclohexane will have even lesser ring strain in comparison to cyclopropane, cyclobutane and cyclopentane. Hence, out of all these 4 cycloalkanes, the highest ring strain will be possessed by cyclopropane and the lowest ring strain will be possessed by cyclohexane. That is why out of all these 5 options, you will have to choose option B, which is listing the cyclohexane as the lowest ring strain and cyclopropane as the highest ring strain. Okay. So now we have this question. Which of the following statements is a correct description of the most stable conformation of 1,1,3 trimethyl cyclohexane? So, a cyclohexane conformation you will have to draw, where you will have to place 3 of the methyl groups in 1,1,3 position. Okay. So, if we draw 1,1,3 trimethyl cyclohexane, for the methyl groups which will be present in the first position, one of it will be axial and the other will be equatorial. Okay. So now you will have to place the third methyl, the methyl at the third position, in such a way that it minimizes steric hindrance or 1,3 diaxial interactions. Okay. For that, you know that the third methyl must be contained in an equatorial fashion. So here I have shown 2 different conformations which will be possible for 1,1,3 trimethyl cyclohexane. So in the first structure, if you notice, there are 2 methyl groups. in the first position, okay, out of which one will be axial and the other will be equatorial. And in this first structure, the methyl group at the third position is in axial. Now let us move to the second structure. In the second structure, we have noted this carbon as the first carbon, and here also one methyl is axial and the other methyl is equatorial. So in this one, the third methyl group present in the third carbon is kept in an equatorial fashion. So out of these two possible conformations, the first one will have a very high 1,3 diaxial interaction, because this methyl is also present in an axial fashion. So this will have 1,3 axial diaxial interaction with this methyl group as well as the hydrogen group present at this carbon. Okay, so this is why this 1,3 diaxial interaction will make the first structure highly unstable. Whereas in the second structure, if we see, only one methyl group is in axial and the other two methyl groups are in equatorial. Hence, now we will go back to the question and read the statements. Okay. So the first one says the methyl group at C3 is equatorial. Yes, in the stable conformation, the third position methyl group is equatorial. Option B says C1 is a tertiary carbon and C3 is a primary carbon. Okay, C1 is a tertiary carbon, but C3 is not a primary carbon. It is attached to three different alkyl groups. Hence, we cannot call it as a primary carbon. Option C says C1 is a quaternary carbon and C3 is a secondary carbon. Okay, here again C1 is a tertiary carbon. So option C is also a wrong statement. Option D says C1 is a tertiary carbon and C3 is a secondary carbon. No, in this case, all the three carbons are tertiary carbons. Or both the carbons are tertiary carbons. And in option E, it says both methyl groups at C1 are equatorial. No, that is not possible. In cyclohexane conformation, any substituent at one ring carbon will, one of the substituent will possess axial position and the other will occupy equatorial. Both the methyl groups cannot occupy equatorial position. Hence, option E is also a wrong statement. So, out of all these 5 statements, the first statement is the correct one. I hope this is clear to you. Okay, so let us move to the next questions. Which of the statements below correctly describes the chair conformations of trans 1,4-dimethyl cyclohexane? So now you will have to draw the chair conformation of trans 1,4-dimethyl cyclohexane. So the statements are the two chair conformations are of equal energy. The higher energy chair conformation contains one axial, one equatorial methyl. The lower energy chair conformation contains one axial, one equatorial methyl. The higher energy chair conformation contains two axial and the lower energy chair conformation contains two axial. Let us now try to draw the chair conformation of trans 1,4-dimethyl cyclohexane. So in this case also, there are two possible conformations. for trans 1,4-dimethyl cyclohexane. In first possible conformation, if we notice, both the methyls which are in 1,4 trans position, they are occupying both the axial positions. Whereas if you rotate it, we are going to get another conformation of trans 1,4-dimethyl cyclohexane, where this time the methyl groups will occupy the equatorial positions. As we know that the bulky substituents, be it methyl, isopropyl, ethyl, all of these will prefer to occupy equatorial position to eliminate steric hindrance or 1,3-diaxial interactions in molecules. Hence, out of these two possible conformations, the second one will be more stable one, as both the methyls are in equatorial, whereas the first conformation will be the least stable one or unstable one, because both the methyl groups are occupying axial positions, and hence both of these will have independently 1,3-diaxial interactions. Hence, if we go to the statements, now we know that both the conformers are not of equal energy, and the higher energy chair conformation is the one which will contain both the methyl groups in the axial position. Okay, so out of all these 5 statements, you will have to choose the fourth statement as correct, because it says the higher energy chair conformation contains 2 axial methyl groups. So the next question is also talking about the chair conformation of another molecule. So it says, which of the statements below correctly describes the chair conformations of trans 1,3-diethyl cyclohexane? So the molecule in this question is having 2 ethyl substituents in 1,3 position, and both you have to place in trans fashion. Okay, so let us try to draw trans 1,3-diethyl cyclohexane, which will have again 2 conformations. So the question is for ethyl, but I have shown the example with methyl. You just have to consider an ethyl group in place of the methyl groups, but the energies concepts will be the same. Okay, so for trans 1,3-diethyl cyclohexane, the first possible conformation will be this one, where one methyl group will be in the axial position, and the methyl at the third position will be in equatorial position. After that, another conformation is possible for trans 1,3-diethyl cyclohexane, where methyl group in the first position will be in equatorial position, whereas the methyl group at the third position will be in axial position. So in both the cases, one methyl group will be in axial position and the other methyl group will be in the equatorial position. Hence, the amount of 1,3-diaxial interaction in these molecules will remain the same. Okay, this is why we can conclude that both conformers will have the equal energy and hence they will be equally stable. Now let us go back to the statements which are given in the question. It says the two chair conformations are equal in energy. Yes, that is a correct statement. And further statements are saying that the energies are not identical. Rather, one of these will have higher energy or one of these will have lower energy. Hence, we will eliminate the other options out of the 5 statements given, and option A will be the correct one. Let us move to the next question, which is now going to talk about the different conformations of cyclohexane and their energy. So this will involve the energy profile diagram for cyclohexane conformations. I hope you remember the different conformations for cyclohexane, which were chair, half chair, boat and twist boat. So for reference, I have listed down the possible conformations for cyclohexane. If we start from the chair conformation A1 and move to the half chair conformation, you have to note down that the half chair conformation is having such a steric repulsion that it is having 43 kilojoule per mole energy in itself. Now, if we move from the half chair conformation to twist boat conformation, the energy now decreases from 43 to 21 kilojoule per mole. Further movement from the twist boat to boat conformation slightly increases the energy from 21 to 25 kilojoule per mole. Okay. Hence, if you look at all the 4 possible conformations of cyclohexane, you can clearly see that half chair will have the highest energy, and hence this one will be the most unstable conformation of cyclohexane. Whereas chair conformation is the one which is the most stable conformation for cyclohexane, having a 0 minimum energy. So, if we go back to the options, we will have to choose option D because it ranks the conformations as chair less than twist boat less than boat, and which is less than half chair conformation. I hope the energy values are clear to you. Now, let us move to the stable conformations of these 2 organic molecules given. Okay. So it says, draw the most stable conformation of cis-1-ethyl 3-methyl cyclohexane and cis-1-ethyl 4-isopropyl cyclohexane. So you have to draw the most stable conformation of cyclohexane, where you have to put, in the first question, you will have to put 2 different substituents in 1 and 3 position. In the first position, you will have an ethyl substituent, and in the third position, you will have a methyl substituent. And similarly, in the second question, you will have ethyl substituent in the first position and isopropyl substituent in the fourth position. So let us solve these questions one by one. Okay. In the first question, we have 2 alkyl groups, 1 ethyl, 3 methyl. So out of these 2 alkyl groups, ethyl is more bulky, okay, because it is having an extra carbon atom. Hence, if we have to place any of these 2 in axial position, we will not place the bulkier one in axial, because it will cause more prominent 1,3 diaxial interaction. Okay, so if in any case we have to put one substituent in axial position, it must be the smaller one. Okay, so if we draw one ethyl 3-methyl cyclohexane, you will get to see a chair conformation of this type, and since it is mentioning cis, hence both the substituents will be placed in equatorial positions. Note down that if the question asked trans 1-ethyl 3-methyl cyclohexane, in that case we would have put the methyl substituent in the axial position. Okay, so I hope this structure is clear to you. Next we have the most stable conformation of cis-1-ethyl 4-isopropyl cyclohexane. Again we have two different substituents. One is ethyl and the second one is isopropyl. So out of ethyl and isopropyl, isopropyl is bulkier. Hence, in any case, if we have to put one of these two in axial position, it must be the ethyl one, because we cannot put the bulkier one in the axial position. It will lead to more 1,3 diaxial interaction or more steric repulsion. Okay, and since this is given cis 1-ethyl 4-isopropyl, the structure will somehow look like this. So in this case, both the substituents are in 1,4 relative position, and it is given as cis. So if we have to put the substituents in the same phase, one of these two must be in the axial position. Okay, and like I said, you cannot place the bulkier substituent in the axial position, so we are choosing ethyl substituent to be the axial position. So this is why the most stable conformation of cis-1-ethyl 4-isopropyl cyclohexane would somehow look like this. Okay, so in the next question, in the lowest energy chair conformation of cis-1,3 dimethyl cyclohexane, how many axial positions are occupied by hydrogen atoms? So for that we are given 5 options. Let us try to draw the most stable conformation of cis-1,3 dimethyl cyclohexane. So in this case, you have to note down that both the methyl substituents are in 1,3 position and they are cis. Hence, in the lowest energy one, both of them will occupy the equatorial positions. Okay. So out of these two conformations which I am showing here, the lower one, the one which I have shown here, this one will be the lowest energy chair conformation, because both the methyl groups are equatorial position. So as the question asks, how many axial positions are occupied by hydrogen atoms? So since both the substituents are occupying only equatorial positions, all the 6 carbon atoms of the ring will have axial hydrogen atoms. Because suppose we are talking about this carbon atom, this will have one axial, one equatorial hydrogen. This will also have the same. This will have an axial hydrogen. This will also have one axial, one equatorial, and this one will have one axial, and this one will have one axial, one equatorial. Hence, in total, all 6 of the axial positions will be occupied by hydrogen atoms in the lowest energy chair conformation. Hence, you will have to choose the option E as the correct answer in this question. In the next question, in the lowest energy conformation of the compound below, how many alkyl substituents are axial? So, we have 3 alkyl substituents present in the given structure. Let us look at the most stable conformation, which will be the lowest energy conformation, and we will see how many of these will be in the axial position. Okay, so note down then that the positions of these alkyl substituents are 1, 2 and 4. So if we draw in such a way that the 2 and 4 position substituents are in cis fashion, which means they will be in the same phase. Okay, so we will have to put the alkyl substituents in this fashion such that the methyl group will be in the opposite phase of the from the other two substituents, and the other two substituents will be cis to one another. And you have to note down that the bulkiest substituent here, which is the isopropyl, it has to be equatorial. Okay, because if you place it in any of these axial positions, this will cause enormous steric congestion in the molecule. Hence, it will be highly unstable. So, if we are talking about the lowest energy conformation, the isopropyl group must be present in a equatorial position. So, you can start drawing it by first placing the isopropyl group, and accordingly you can place the other two substituents in cis or trans with respect to the isopropyl group. I hope the structure was clear to you. Now here we have another question where we again have 4 different cyclohexane conformations, and you have to choose the most stable conformation given for the mentioned structure, okay, the mentioned molecule. So as you can see in the structure, we will have an exomethylene group in the first position, and this double bond is also having these 2 methyl substituents on the other side of the double bond. Moreover, in the second position of the cyclohexane ring, we can see the presence of a methyl substituent. Okay, so we will have to place these 2 ring substituents, one of which is exomethylene and the other is methyl group. We will have to place them in such a way that the structure will have the least steric congestion in the conformation. So if we look at the options given, in the first option we can see that apart from the double bond, the methyl substituent is present in equatorial position. And in the second option, the methyl substituent is present in an axial fashion, which will definitely cause very high 1,3 diaxial interaction. In the third option again, we can see that the structure overall is not in the most stable chair conformation way, rather it is in a boat shape. Okay, it is having the boat conformation of cyclohexane. And in option 4 again we see that the structure given is not in the most stable conformation of cyclohexane, which is the chair conformation, rather it is in a twist boat fashion. So now we have an idea already that out of these 4 options, we can directly eliminate the option 3 and option 4 because these two are having boat and twist boat conformations which are very unstable as compared to chair conformations. But if we talk about option 1 and 2, we will have to note down all the possible 1,3 diaxial strains. Okay, so for the first structure, if we see, we are going to have steric repulsion between this methyl group and this methyl group of the carbon-carbon double bond. Similarly, on the other side of the double bond, this methyl substituent is going to have a steric repulsion with this hydrogen present in the adjacent carbon. So, this is the total energy possessed by the conformation given in the first option. And if we move to the second structure, we can see that here also the methyl group will have 1,3 diaxial interaction with both these axial hydrogen atoms. Although this methyl will not have any steric interaction with the double bond substituents, but it will have a steric repulsion with the hydrogen atoms which are axial. Okay, so if we calculate the total energy possessed by the structures given in option 2, we see that it contains 2,1,3 methyl hydrogen axial interaction, which gives the amount of energy to be 1.8 kilocalorie per mole. Hence, out of option 1 and 2, we will have to choose 2 as the more stable conformation because it is having less energy than the first one. And like I already talked about option C and D, they are having a boat conformation and twist boat conformation. So they are already unstable than both the chair conformations possible. So in this question, option 2 will be the correct one. I hope this is clear to you. Next, let us move to the next question. Here, we are given 2 decalene molecules, okay? And both these 2 decalene molecules are having 2 methyl substituents in the junction carbon atoms. So, you have to choose the correct statement about the following compounds. So, it says whether A is more stable or B is more stable or both of these are equally stable. Let us one by one calculate the energies contained by both these 2 structures given, okay? So here I have listed down all the 1,3 diaxial interactions possible in A and B. And the structure B will also be having gauge interaction. So, if we consider the number of 1,3-diaxial interactions, you will see that both these compounds are having equal number of 1,3-diaxial interactions. Okay, so these 8 possible 1,3-diaxial interactions will make both these molecules equally stable, and both the molecules will have equal amount of energy because of equal number of 1,3-diaxial interaction in themselves. So you can note down the possible interactions. Okay, so let us move to the next question, where we have to identify the most stable conformation for the following compound. So we have another cyclohexane molecule in which we have placed four substituents, two of which are hydroxyl groups and the other two are tertiary butyl substituents. So we are given two chair conformations and two twist boat conformations. Two chair conformations and one twist boat and one half chair conformation is given. Hence, let us identify the more stable conformation given for the molecule. In the third option, which is given to be the twist boat one, in general, as we have seen that whenever we have substituted cyclohexane molecules, the more stable conformations are the one where the substituents are placed in equatorial positions of a chair conformation. Okay, but the molecules which are exceptions, like the one which is given in this question, here we have a possibility of hydrogen bonding in the molecule in between the substituents. Okay, we have two hydroxyl groups, so the most stable conformation will be the one where we will have a possibility of hydrogen bonding, because you must remember that hydrogen intramolecular hydrogen bonding leads to lowering of a huge amount of energy. Hence, although we had options where we had our molecule in chair conformations, because of the possible intramolecular hydrogen bonding, option 3 will be the most stable conformation, which will be shown as shown here. Okay, I hope this is clear to you. Now let us move to the next question. So here we have the structure that corresponds to the most stable conformation of the following compound is. So we have a dioxane molecule given in this question, and it is tetra substituted, and it is a 1,4-dioxane molecule. Okay, we have tetrachloro substituted 1,4-dioxane molecules. So it is given in 4 different conformations, and you will have to choose the most stable conformation. So in structures like this, you have to consider the concept of anomeric effect. Let us revise the anomeric effect. So you can understand this effect as the heteroatom present in the ring will be placed with respect to the carbon and heteroatom bond in such a way that the ring heteroatom can donate its electron pairs to the sigma star antibonding orbital of the carbon heteroatom bond. Okay, so as you know that carbon heteroatom bond is a single sigma bond, so it will have two molecular orbitals. One will be sigma bonding and the other will be sigma star antibonding. So if the atomic arrangement in the conformation will be achieved in such a way that we can donate electron pairs to the sigma star antibonding orbital of the carbon heteroatom bond, that can lead to stabilization of the conformation. Okay, and the ideal placement for the heteroatom in the ring and the carbon heteroatom bond comprises of the axial position of the carbon heteroatom bond as shown here. Okay, although we know that the placement of the substituents in axial position can lead to 1,3 diaxial interactions. In examples like this, you must understand that anomeric effect brings a very high stability to the molecules. Hence, if there is a possibility of attaining stability via anomeric effect, you have to place the carbon heteroatom bond in axial positions so that electron donation from lone pair to sigma star antibonding is possible, and that will lead to the conformation to be more stable. So, in all these four options, we will have to choose that option where all the carbon heteroatom bonds are in axial fashion so that the maximum anomeric effect stabilization can be attained. Okay, so out of these four options, option 4 will be the correct one because all the carbon chlorine bonds you can see are in the axial position. So all these four carbon chlorine bonds will have one sigma star antibonding molecular orbital for all these four bonds. So the lone pair of electron donation from oxygen to the sigma star antibonding will be possible for all these four substituents. I hope this anomeric effect concept was clear to you. So this question you can note down as a practice question where we have a Newman projection given and we are given four options here. So you just have to break down the Newman projection structure into a simple planar structure. For that, you will have to keep your eye here first and you can imagine, suppose we are talking about the first option, you can imagine this CH2 to be this one and this CH2 to be this one. Okay, hence at the first glance we know that this cannot be the correct option. Okay, so I will tell you the correct option, but you can break down the Newman projection into the correct structure. Okay, So if you step by step break it down, you will achieve at a structure which will be this one. Let us move to more complex questions. So we will now talk about a few more exceptional conformations which will not follow the placement of substituents as the conventional way, which talks about placing the substituents in equatorial position. Rather, there will be various stabilizing factors in different conformations, due to which we will get some other conformation to be the most stable one. Okay, so in such cases, stabilizing effects like anomeric effects, hydrogen bonding, etc. comes into the picture. So let us take the example of this compound which is given. Among the structures given below, the one that corresponds to the most stable conformation of compound A is. So compound A is now a 1,3-dioxane compound, and in this 1,3-dioxane ring we have two substituents, okay, one of which is methyl and the other is hydroxy. So the methyl group, which is a alkyl group, that will undoubtedly occupy an equatorial position to minimize steric congestion or 1,3-diaxial interaction. But in this case, hydroxyl group will occupy a position which will attain stability towards the conformation because of intramolecular hydrogen bonding. Okay, so this will look somewhat like this. Both the ring dioxane ring oxygen atoms will participate in intramolecular hydrogen bonding with the hydroxyl group. Hence, the most stable conformation for the given molecule will be the one where the methyl group is occupying the equatorial position and the hydroxyl group is occupying the axial position to facilitate hydrogen bonding with both the ring oxygen. So another similar question we have here. Here we will talk about the most stable conformation of 2-fluoroethanol. So out of these four given conformations, you have to choose the most stable conformation. So if you look at option 2 and 3, conventionally we would have chosen the option 4 because this is showing both the substituent in anti fashion, okay, but in this particular example, fluoroethanol will involve stability via intramolecular hydrogen bonding. Hence, this kind of hydrogen bonding will be possible in option 2 and 3. But option 3 is having a eclipsed conformation. So in this one, although it will have a stability via intramolecular hydrogen bonding, the close proximity of both the substituents will also cause steric repulsion among themselves. Hence, the more preferred conformation will be the second option conformation, because this is having a Gauch conformation and the substituents will have an intramolecular hydrogen bonding possible. Hence, it will be stabilized via hydrogen bonding, and it will also not experience significant steric repulsion. So, the correct option will be option B. Now, let us move to the next question. Among the following, the most stable conformation of meso 2,3-dibromobutane is. So, in meso 2,3-dibromobutane, if we draw the Newman projection, in the most stable conformation, we will have to place the substituents in such a way that both the methyls must be anti to each other, as well as both the bromides will also be anti to each other. Because otherwise, if we do not place them in anti fashion to each other, it can cause very, very high amount of steric repulsion among themselves. Hence, this particular conformation will be the most stable one for meso 2,3-dibromobutane. And when we talk about the stability of such conformations, steric hindrance plays a very big role in deciding whether it will be stable or unstable. Okay, so I hope this question is clear to you. Now we have another question where it is asking, why is conformational analysis important in drug receptor interactions? So the options given are: only chemical formula matters for binding, bioactive conformation dictates how a drug fits and binds to a receptor, it determines melting point only, or it predicts pH of the drug solution. So we are going to understand this question using the example of R-thalidomide and S-thalidomide. So thalidomide is a drug which was used to treat various uncomfortabilities in caused during pregnancy. So in that case, the R-thalidomide was the enantiomer which was used for diagnosis. Okay, but the other enantiomer, which is having the exact same molecular chemical formula, and it differs only in the stereogenic center at this position. This S-thalidomide has teratogenic effect. That means it can cause birth defects in babies. Okay, so it is very interesting that one enantiomer of the drug is being used as a medicine, whereas the other enantiomer can cause birth defects in infants. Okay, and both these two molecules are differing at one single position. So that is how conformational analysis plays a very important role. And one slight difference in conformation can dictate how drug can fit and bind to a protein receptor. Okay, this is just an example. So if we go back to the question, if we talk about the options, we will have to choose option B as the correct answer, because bioactive conformation dictates how a drug fits and binds to a receptor. Okay, and hence conformation plays a very important role in drug binding chemistry. Now we have another question. Which descriptor quantifies the orientation between four sequentially bonded atoms? So it simply asks the orientation of the plane which is having four sequentially bonded atoms of a molecule. What will it be called? Is it a bond length? Is it a bond angle? Is it a dihedral angle, or is it van der Waals radius? So before solving this question, I hope you know that bond length will involve a bond present between two atoms. A bond angle will involve three atoms and the bond between these three atoms. The angle between the bonds of these three atoms. The dihedral angle will in fact involve four sequentially bonded atoms, and it will involve two planes which will involve the dihedral angle. And van der Waals radius will require the radius of a spherical entity. Hence, for this question, we will have to choose option 3 as the correct answer. This simply comes from the definition of the dihedral angle or torsional energy. Then in the next question, in substituted cyclopentane, envelope and twist conformations exist to reduce pi stacking, angle and torsional strain, ionic interactions, or covalent bond strengths. So, the envelope conformation for cyclopentane exists as the most stable conformation so that it can minimize the angle strain and torsional strain in a cyclopentane ring. Okay, so out of these four options, we will choose option B as the correct one. In the next question, we have which change converts one stereoisomer into another and is not a conformational change? Rotation around a single bond, ring flip of cyclohexane, breaking and reforming bonds, for example, inversion at a stereocenter, rotation about a C-N single bond without bond cleavage. So we are given these four options. We have already talked that when we are talking about conformational change, we are not going to involve any bond formation or bond breaking. We will be rotating the molecule via a carbon-carbon single bond. And hence, rotation is common in conformational changes. But breaking and reforming bonds is not allowed when we are talking about conformational change. Okay, hence out of these four options, we will choose the third option, which is saying that breaking and reforming bonds will also be which will not be a conformational change. Yes, so we are going to choose the option 3 as the correct one. Next we have, which factor does not directly affect conformational preference? Option 1, steric interactions. Option B, electronic effects. Option C, solvent polarity. And option D, atomic mass number. So it will again come from the theoretical definition of conformational preferences. And out of these four options, we'll have to choose the option 4, which is atomic mass number, as the correct option, because it does not have to do anything with conformational preferences. Whereas, as we have seen, certain conformations will be preferred due to steric interactions or electronic effects, like we saw in case of fluoroethanol, or even solvent polarity. Certain conformations will be more easily soluble in certain solvents, okay, but atomic mass number will not have any role to play with conformational preference, because it will remain constant for all the conformations possible for a given molecule. And the next question says, choose the correct statement. First option says conformation of proteins depends only on environmental factors. Conformation of proteins is affected by environmental factors. Conformation of proteins does not depend on environmental factors, or conformation of proteins depends only on the amino acid sequence. So you must know that when it comes to conformation of proteins, it is affected by environmental factors, like we just now talked about solvent polarity. Certain conformations are more preferentially formed in certain polar or non-polar solvents. Hence, conformation of proteins is affected by environmental factors, but it does not depend only on environmental factors. There are more things which play major roles when it comes to conformation of proteins. Okay. Hence, out of these four options, we'll choose option B as the correct option, which says as conformation of proteins is affected by environmental factors. So, some of the environmental factors which influence the protein conformations are temperature, pH, and humidity. So, I hope this is clear to you. So, with this, we have solved the questions of today's tutorial. Let us quickly go back and pass through all the questions which we have solved today. Okay, we started with the theory part of conformations, where we talked about that conformations are different arrangements of atoms that can be converted into one another by rotation about a carbon-carbon single bond. Then we also talked about torsional energy and potential energy diagram of N-butane. We also talked about various conformations of butane, and we also talked about ring strain in cycloalkanes. Next, we talked about the most stable conformation of 1,1,3-trimethyl cyclohexane. We had also talked about the most stable conformation of trans 1,4-dimethyl cyclohexane. as well as trans 1,3-diethyl cyclohexane. Then we went through the energy profile diagram of cyclohexane ring, and we saw that the chair conformation will have the lowest energy, whereas the half chair conformation will have the highest energy. We had also drawn the most stable conformation of cis 1-ethyl 3-methyl cyclohexane and cis 1-ethyl 4-isopropyl cyclohexane. And we had also tried to draw the cis 1,3-dimethyl cyclohexane, and we figured out how many hydrogen atoms in total are present in the axial position. Then we also tried to draw the most stable conformation of this cyclohexane ring having 3 different substituents. And after that, we solved this question where we talked about the most stable conformation of the given molecule. So we first eliminated the option 3 and 4 because of having both and twist boat conformation. And out of 1 and 2, we figured out that option 2 is having the least energy because of less number of 1,3 diaxial interaction. Then we also compared the energies of these two trans and cis decalene, and we figured out that both of these are having equal number of 1,3 diaxial interactions. Then we talked about the most stable conformation of this given molecule, and we saw that despite having a twist boat conformation, option 3 was having the minimum energy because of intramolecular hydrogen bonding. After that, we talked about anomeric effect, and we understood the concept of anomeric effect, why it brings stability to the conformations. And out of these 4 possible options, we saw that the one in which all the carbon heteroatom bonds are placed in axial position was the most stable one. Then we solved another question of this 1,3-dioxane, where one methyl substituent we placed in the equatorial fraction, whereas the hydroxy substituent we placed in axial position to have the intramolecular hydrogen bonding stability. And then we also talked about the most stable conformation of 2-fluoroethanol and meso 2,3-dibromobutane. After that, we solved these theoretical questions about conformational analysis. And we saw how bioactive conformation dictates how a drug fits and binds to a receptor. And we had also talked about dihedral angle and how in substituted cyclopentane, envelope and twist conformations exist to reduce angle and torsional strain. After that, we again revised that there is no breaking and reforming bond allowed when we are talking about conformational analysis. And then we also went through the factors which directly do not affect conformational preference. And lastly, we talked about how conformations of proteins is affected by environmental factors. So with this, we have solved all the questions for today's tutorial on the topic conformational analysis. I hope the concepts were clear to you. So we will meet on next Friday for the next tutorial of the course. Thank you very much for joining for today's tutorial.